Good afternoon, everyone. My name is Sela. I'm the Director of Development for the College of Engineering, and I support the Dean in our corporate partnerships. Today, it is my honor to introduce our speaker. Dr. Simon is the Deputy Lab Director for Research and Chief Research Officer of Lawrence Berkeley National Laboratory. He serves as management liaison to the University of California, the Department of Energy, and other public and private agencies and programs to represent the laboratory's programs, accomplishments, and initiatives. As a deputy, he is directly responsible for the management of discretionary research programs at the labs, technology transfer, government affairs, research development, sustainability, and strategic planning groups at the lab report to him. That is a lot of things.
Yep.
He is internationally recognized expert in computer science and applied mathematics. His algorithm research efforts were honored with the 1988 and 2009 Gordon Bell Prize for Parallel Processing Research. He was a member of the NASA team that developed the NAS Parallel Benchmarks, a widely used standard for evaluating the performance of massively parallel systems. He is co-editor of the biannual Top 500 list that tracks the most powerful supercomputers worldwide, as well as related architecture and technology trends. And he holds an undergraduate degree in mathematics from the Technical University in Berlin, Germany, and a PhD in mathematics from UC Berkeley. Please give him a round of applause as he comes up here to address us.
Thank you for a great introduction. So, since you mentioned the NAS Parallel benchmarks, I'd like to point out that my good old friend and collaborator on the NAS Parallel benchmarks, Rod Fortui, is sitting here up front. So, we've been working on this in 27 years ago, 1990, 1991. A long time ago, but it was an important accomplishment. So, I'm at Lawrence Berkeley National Laboratory, and I have to sort of put an emphasis on the Berkeley because there's Lawrence Livermore and Lawrence Berkeley, and we are sister labs. I'll say a little bit more about the history in a moment, but we're in Berkeley, California, up on the hill behind the University of UC Berkeley campus. On my very last slide, and I'll save this so that you don't run away, I'll say a little bit about our student and outreach programs. And it shouldn't be that hard for you to get to Berkeley, because if you figure out a way to go to the Warm Springs or Fremont BART station, it is only 30 minutes on BART to get to Berkeley. So with that up front, what I would like to do is talk a little bit about the lab and then talk about some computing trends. So I do want to say a bit about the national labs, because the national labs really are a very unique structure in the scientific enterprise in the United States. And in Berkeley and I think in many other places, we have many international visitors who try to understand how the national labs fit in, because they have very unique capability that actually strengthens science in the US. And we are doing several things. We're doing basic discovery science. So you see a picture there of Saul Perlmutter, who was the most recent Nobel Prize winner for work that he's done in cosmology. And his work in the mid-90s was really the discovery of the expanding universe, and he used supernova to make this measurement. So that's an example of very basic discovery science. We're doing discovery science to address national challenges. Being part of the Department of Energy, of course, we're looking at energy challenges, environmental challenges. And so we're using these unique scientific capabilities in addition to the basic science also to do applied science and always look at how can we impact industry. And so another example here of the pictures of Paul Alivasaurus, our former lab director in the National Medal of Science and Technology that he received for discovery in nanoparticles that were licensed out, and they were licensed. There was a startup company, it's actually in Fremont, called Nanosys, that then developed that technology, and it ended up in very high definition TVs in bright screens. So Kindle Fire is using that technology. Samsung is using that technology. So this is from basic science to applied science. We have very large research facilities, and of course, one of our missions is to reach out and bring science, technology, engineering, mathematics students like yourself to the lab and learn about some of those big challenges. And so, as I said, I hope that I will maybe get the interest of some of you think about Berkeley Lab. I do want to show this old slide because it tells a number of stories. So this is a very famous slide going back to the 1930s. The lab was created in 1931, and it's now more than 85 years old. It's one of the oldest national labs. Ernest Orlando Lawrence, who sits up front here, was the founder of the lab, and he was the first person to build particle accelerators. He had sort of this idea of building accelerators in a circular way. Cyclotron was basically his invention. And there are a couple of things you can tell about this, and I want to tell maybe two things here. One is Ernest Orlando Lawrence did not get tenure at Yale, and then came to Berkeley, and Berkeley hired him, and he didn't get tenure at Yale because Yale was, I can say this here, a stuffy East Coast liberal arts university that was not interested in physicists who are actually going out and were sort of in the lab and working with real engineers, like the folks here, to build big things. That was just not the thing that was done in academic physics in 1920s and 30s. So Lawrence built this, and the cyclotron was the foundation for a lot of work in high-energy physics and nuclear physics. And several of the early collaborators that you see in this picture went on to launch very important, successful careers on their own. For example, Oppenheimer, who is up here with a pipe, he went on to become the director of the Manhattan Project and started basically the Los Alamos National Lab, which was an essential element of the nuclear weapons technology that was really important during the Second World War. Others you have here, like Wilson, he went on to Chicago and Fermilab. You have Alvarez in this picture, who won the Nobel Prize in nuclear chemistry, but is known for having made the discovery that the dinosaurs got extinguished by a big meteorite impact, and so on. So there's a lot of history in this, but I think for the Bay Area, it's also important to keep in mind that those folks, and I always say that Lawrence in Berkeley and Terman at Stanford sort of changed this and introduced an applied culture, just like Berkeley had an incredible impact on the history by developing the Manhattan Project. The same thing is true about Stanford and Terman and the engineering development at Stanford that created Silicon Valley as we know it today. So it was about 100 years ago in the 1920s to 1930s that really, because of basic science, the foundation of Silicon Valley was created. There are two other things I want to say. One is that it is about big science, so they're here to build big instruments. That's still what we're doing at the lab. I'll say a little bit more. And it's about integrated teams. We're trying to have really everybody working together on this, from the physicists to the engineers to the financial people. And this being, of course, from the 1930s, it's not a diverse team. And unfortunately, let's say you see all white male in suits on top, and I hope we have a more diverse picture now. I think we do, but it's still another issue where we need to address. But otherwise, a lot of the origins of the lab are in here. So where we are today, just very quickly, we are a big national lab. We run these big facilities. NERSC is the computing facility. I was director of that facility for almost 10 years before I moved on to my current job. These facilities are open for everybody. So if you're faculty and you have a scientific project, say nanoscience or a synchrotron light source, that's for you to use. NERSC, the computing resources there. These are large-scale instruments that everybody can use. So they are also available, even if you don't have a Department of Energy contact, you can apply and use these. We're also very tightly integrated with the University of California. This is some measure of integration, not just with UC Berkeley, but we have programs with Merced and Davis and UCSF. And one of the many reasons I'm here is because I think that San Jose State students, in particular in the engineering and technology and math fields, have a lot to offer, and I certainly want to make a bigger outreach to San Jose State. Race for visibility. I know we're 40 miles to the north of 45 miles. That's maybe too far, but it's still reachable, and so that's what I want you to leave with, that there is a place that you should consider. So these are the big facilities. I don't want to say much more about them. We can talk about this in more detail later. I want to very briefly say what are the thrusts at the National Lab. I talked already about the discovery science, discoveries in fundamental science like the cosmology. The upgrade light source is a synchrotron that we're upgrading to have a very high resolution that can be used to explore materials to great detail, but also look at biomolecules. I'm, as I said, a computing person. I'll talk a little bit more about exascale. That's the next stage in high-performance computing that we can use to do computational simulations. And we're doing a lot of work in biological and environmental science using biology to solve environmental problems, for example, biofuels. But something that's very fascinating, I don't want to say much more about it, but if you're in, say, bioscience or environmental sciences, we really don't understand at all what's happening in the soil. And there are microbes in the soil. The soil microbiome is as complex as the human gut microbiome. And we don't know what those microbes are doing. You may be familiar with in medical science that the insights that your body is full of microbes and they are part of your system. They belong to you. They help you digest and everything else. The same thing is true about our environment. We don't know what those things, what those bugs are doing. And then we could maybe make those microbes help us in solving environmental problems or making plants grow faster. So these are all projects that are associated with these thrusts. Can talk about many of these. The one I was talking about, Enigma, is trying to understand the microbes in the soil, for example. But what I want to focus on is some of our research initiatives. The initiatives are 3 to 5 years. These are currently hot topics. These are the current initiatives. If you're in any topic, in any of these topics interested in, for example, I think water and energy is an important topic, and you know that is a regional problem, so solutions that are found in California may not be the solutions for the Midwest. Cleaning up drinking water in Flint is different from understanding how we best use the scarce water resources in California. That's what this group is looking at. But what I would like to talk about is the 3 computing themes that are in these initiatives. And as you heard, I'm a computer scientist, mathematician become computer scientist, and I'm now managing this portfolio. So you might say, well, you put a computer guy in charge of all the funding, and then all the funding goes into computing. That's not what's happening. What's really happening is, and I think that's a very important thing for you to keep in mind, is that I would say over the last 10, 15 years, there was really a change in the approach from all scientists in terms of using computing. So computing is an indispensable tool in all the sciences. We have 20 different scientific divisions at the lab, and every single one is doing significant work in computing. So it's an essential tool today. So I want to talk about beyond Moore's law, quantum computing, machine learning a little bit, and these are probably topics that you are very interested in. Again, I like history. This is another historical slide just to reflect on where we are today. So quite often you hear all this excitement about machine learning and their computers who now play better than humans in Go and then self-driving cars. But it is important to go back and think about 70 years back. So 70 years ago was in the late 1940s, the early development of computers the way we know them today. And in particular, John von Neumann, who is here on the left, he developed the von Neumann architecture for solving large computational physics problems. The driver for the initial computing development was actually large-scale computational physics, that is defense applications. And the architecture that von Neumann, and here's Robert Oppenheimer, whom I mentioned before, which was developed, was really driven by physics. And to be very blunt here, what we have is the origins of computing are back again in the Manhattan Project. We went from the mushroom cloud, unfortunately, to now the cloud. And so what you've got to keep in mind is that this was an architecture that was set up for doing something which was large, say grid-based, floating point calculations. The same architecture is still today in your mobile device. In anything you're doing today, that's the same architecture that you're using for music, for social networking, for watching videos. And it's actually pretty much amazing that there was no change over 70 years in the architecture. And the reason why that was because Moore's law sort of made us lazy with respect to architecture. As you probably know, Moore's law, formulated by Moore in the late 60s, postulates that performance, actually the number of transistors per chip roughly is doubling in an 18-month time frame, and this was consistent for decades. And so if you have this ongoing performance increase, you don't have to really think about how to build a computer. You just take the same chip and make it faster, put more transistors, make it smaller, and therefore more powerful. So this was exponential growth, which happened for a long, long time. Now, exponential growth cannot go on forever. And while this is still maybe in some quarters controversial, we're hitting today an end of Moore's law. So we're actually in a wonderful time for computing. You say, oh, if you're Intel, maybe you don't want to say that Moore's law is going to end because then the next earning report will drop. But if you're in academic research, it is a great time because the fact that Moore's law is going to end and we cannot sort of write this performance way forward easily as we did in the last 60 or 70 years means we have to think harder, which means there's a job for you, very simply put. So to think about Moore's law, this is, I think, the best way of really thinking about Moore's law is 25 years ago, if you had this equipment, a laptop, a video camera, a Palm Pilot or some equipment, a digital watch, a pager, a Sony Walkman, an old-style cellular phone, and I don't even know what that is. Oh, it's a camera. Oh, yeah, there's a video and there's a real camera, an instant camera. All these electronic devices are now basically in your hand. And so Moore's law really led to that level of integration. And what I'm trying to tell you is we won't have it that easy in the next 25 years. We have to think harder. But imagine if Moore's law would have ended 25 years ago, you would not have that device. You would have to carry all this around if you wanted to carry it all around. Sort of an interesting thought. So what I put out here is our general computing trends. What I'm saying here, and of course, be happy to debate this with you, is we are ending a certain era of computing. That was the era of von Neumann architecture driven, accelerated by Moore's law. We'll see the end of semiconductor scaling, CMOS semiconductor scaling. We will hit energy limits of computing. There are new paradigms in computing emerging, like machine learning, which is very widely spread, of course, and something that creates a lot of excitement. All of this will lead to architectural experimentation variety. That's the key point. And therefore, we are sort of at the verge of having all kinds of new computing technologies. And I would almost say that within 30 miles or 50 miles from this location, from San Jose, probably somewhere somebody is sitting in the proverbial garage and we'll have a technology that 10 years from now will be as important and as influential as, say, the iPhone was. So this is, in pictures, a bit of a roadmap of where I think computing will go. And the important thing to keep in mind is that, first of all, there is the traditional digital computing, and at the very high end, supercomputing. This is basically my field and has been Rod's field all along. We're moving towards the exascale, 10 to the 18 floating point operations per second. So this is the push. This is probably something happening in 3 to 4 years. But I also think that exascale is pushing the current technology almost to a limit. I don't really see us with the same technology that is in this box going to 10 or 100 exaflops. We may get to 1 exaflop, but not much further. So therefore, there are, I would say, 3 or other paths that go in the future. One is going beyond Moore's law, new digital technologies, post-Moore digital. There's quantum computing, and I will say a little bit about quantum computing. Actually, I happen to be today at another event that IBM is putting up on quantum computing. And IBM is really taking this very serious, and they wanted to have some conversation on how do we move quantum computing from the research lab into the commercial world. And there's neuromorphic computing, and you could say this is really looking at the brain and looking at how other computing substrates work, and can we learn something from there and building more low-power computing that is solving different, maybe cognitive tasks. So I'll go through these bars. I'll talk a bit about what we're doing in Berkeley. So this is not a comprehensive talk, but a very local Berkeley-focused talk. But it will give you an idea on where I think the challenges are where we want to go. So exascale, this is an initiative that is pushed for solving the large physical simulation problems. So you could say exascale as the extension of a traditional high-performance computing trajectory going back to the original computational physics work done in the 40s and 50s on the first digital computers. It is an international effort in the sense that exascale high-performance computing has been seen as a competitive technology that is absolutely important for industrialized countries. So Here is a Japanese initiative. There's the DOE initiative, the Department of Energy in the US, and there's this example, China building a new supercomputer. So in the exascale race, actually China has made, like in many other industrial and technology areas, a significant investment. And currently, the two most powerful supercomputers are in China. And this is quite an accomplishment, in particular if a number one system is built almost exclusively with Chinese components. So it's an in-the-country built computer. And this is an incredible accomplishment, but it also shows why all the countries, Japan, Europe, China, US, are interested in it, because the technology has industrial impact in many industries like aerospace, oil and gas, automotive. It has scientific impact. It sets us up for scientific leadership. And of course, it has long-term economic impact. So in the US, our colleagues at Argonne National Labs are on the roadmap to get the first US exaflop computer. This is called A21. It's supposed to be built in 21 by Intel, with Intel technology. So this is a very large project. There are similar large projects underway with our colleagues at Oak Ridge, at Livermore, and I hope that we'll in Berkeley get also an exaflop computer by about 23 or 24. So there is a US plan. There is significant investment, even in the bad budget year last year when President Trump announced his first plans. Exascale computing still had an uptick when everything else was cut. So this is seen as a national initiative. So what are we doing with exascale computers? We're doing all these things. These are applications that are done in Berkeley, and you can pick things out. I think some of you are in materials, some of you might be in genomics and biology applications. I think earthquakes is very interesting, so maybe earthquakes is one I can say a little bit more. What is happening here in earthquakes is to couple the seismic motion of a building with the actual underground simulation of the soil. So as you know, soil liquefies, possibly on an earthquake or if it's under big pressure. And actually there is no coupled simulation that has been done yet to take the building and the soil together. And so these type of large-scale coupled simulations are driving exascale forward. So you'll see that most of them, with the exception of genomics, are all large-scale simulations that are derived from looking at physics models, like from fundamental equations in physics, like Navier-Stokes equations or electromagnetics, Maxwell equation, and so on. The ability to do this is instrumental for making big progress in all these areas, and so this continues to be influential. What is done here has impact on the oil and gas industry, has impact on the aeronautic industry, and many other applications, chemistry. So the interesting thing is, so this is happening at the exascale, which is really, I would say, a very small set of overall the computing spectrum, but it's very strategically important because it sets the agenda for what's happening in many of the industrial, sort of the traditional industrial companies. Now, what's currently happening is that there's a great boom in AI, and you must, if you don't know this, then you probably were not paying attention and were falling asleep, and you have all these statements about artificial intelligence here and self-driving cars there and image analysis happening. So this is a huge boom. So just to make a little bit a simple statement here in terms of AI is a big field. AI has been around for a long time. AI includes some robotics application, as I said, like self-driving cars, scene recognition. There is machine learning, which is a specific way of analyzing data. And one element of machine learning is deep learning, which is using the deep learning algorithms that have, like convolutional neural networks, that have been developed over the last couple of years. So I think the actual excitement happened in deep learning. And the excitement in deep learning happened that there were a number of things that happened just in the last couple of years. And this is that a lot of data became available and the mathematical methods were available that scaled to deal with those big data. So that has been driving the whole field of AI. So what I'm saying here is that in order to be successful in machine learning, you really need a large amount of data. You need the algorithms and you need the big machines. And while there are many commercial applications, there are also scientific applications. Being in a science and research lab, we have a large data, we have a lot of algorithmic work that has been done, and the big supercomputers. That's the Berkeley supercomputer called Cori that is currently about a 30 petaflop system. So we're taking all these things together and have an initiative at the lab to understand how we can use machine learning in science. And this is an example of machine learning in science. It's actually an image analysis. And that's important, and I think there may be many other machine learning applications out there, like how to place ads on your web page, or what you might want to buy next, or if you can discover cat videos on the internet. All these are more or less useful applications. But machine learning is, at this point, already making a significant impact in science. And what you see here is, it's maybe not as well recognizable. This is a global climate simulation. And you see here extreme events. So this is actually precipitation. The extreme events are these little vortices, which are basically hurricanes. And what you have is, if you run a big climate simulation, you have huge amounts of data over many years, 20 years of simulation. 20 years of calendar years of simulation. And you don't want a student to go in and look at those pictures and start counting hurricanes. And so this is a very fundamental science question that is a question that is out there, and this is that assume that the oceans are getting warmer, and what does that do? And there are statements, and well, then we'll have more hurricanes. Well, that's a very high-level statement, and what they've been doing here in this project is to run many simulations with different scenarios of ocean warming and looked at the frequency and the amount of rainfall generated in hurricanes. And there was a very highly touted paper that was just published last December at the American Geophysical Union meeting in New Orleans, which basically said that the hurricanes that we saw last September in Houston, for example, have with high probability 30% more water being poured down than which can be traced back to temperatures in the Gulf of Mexico raised by about 1 degree. So you're doing this type of analysis, and you can only do this if you can do these counts, and you do these counts with machine learning, and there is a more detailed discussion that is done on those big supercomputers. So this is a very simple statement, but it's something you should keep in mind is that the reason machine learning is successful is you have the algorithms that scale, and you have the large data that scale. You need this both. There are sort of efforts to get by with less data, but without the data you have, it's very difficult to have a successful machine learning application. So machine learning is happening currently on the high-end supercomputers, and machine learning is happening for scientific applications. So that's definitely something that has changed also in the national labs. So the next topic I want to talk about is post-Moore digital. And this goes back to Moore's law. So Moore's law, which I quoted already, states that everything is just swimmingly going fine, better, faster, cheaper. And here is basically a statement that, as I said, is debated by many, but not really that much, is that Moore's law will end in 2025. Now, Moore's law will not end sort of like, here's the end of Moore's law, and I step down and everything will collapse. So Silicon Valley will end up like Detroit, and people will go around with posters, will program Python for food or something like this. This is not what it's going to happen. It's going to slow down, and we actually see the slowdown now. I can make this argument because I look at the performance scheme. But there's a very simple way of, there are two ways of explaining why things actually have to change. One is because semiconductor scaling is based on making things smaller and smaller and smaller. And every time you make things smaller, and I just jump to the end, you get at some point to a resolution somewhere between 10 nanometer and 1 nanometer, where you might have more gates than you have atoms in that space. And once you hit that point, you cannot have more gates in a volume or an area of material if you don't have the atoms there. So something breaks down. And we're really approaching this limit ultimately there, but there are many other ways of approaching this limit already. One is that the semiconductor companies are already bit fudging their numbers. So if they say we have 14 nanometers, then that means they'd have some of their wire width is 14 nanometers, but they haven't scaled everything down to 14 nanometer. There is a big issue in terms of lithography that you have to make more and more masks to get to that very narrow line width on chips. And so the cost of making semiconductors has been going up significantly. So we're talking now between $1 and $10 billion for a fab. And so there's an economic factor as well that contributes to the slowdown. So the interesting thing, though, is, and this is something that you hear and you never really put it together on a set of slides. The interesting thing is that everybody's talking about Internet of Things, and you can look at yourself how many processors are on your body right now. So you can do a quick count, how many you have in your pocket, and if you have some other digital device, and how many you have in your laptop. But the fact is that there will be sensors everywhere, and they're all driven by microelectronics, and so there are different studies about what the Internet of Things is going to look like, and people talk about 25 billion embedded intelligent systems, and each one of those embedded intelligent systems will have some processing capability. And so that means that we're going to a point where this is another one of those Internet of Things prediction, where processors are everywhere. And here's some basic math. If you think that these are just milliwatt, it doesn't matter, but billion times nothing is not nothing, that's mathematics. Billion times 0 is still 0. But a billion times a milliwatt is a lot. And that's basically where we're up at. And this is that if everybody believes that we will have those billion types of devices everywhere, there are predictions that by about 25, when all these devices are out there, all these devices take 25 to 30% of our electric power consumption. The interesting thing is we're actually already approaching this in a different space. So I'm pretty sure at least some of you have tracked and are involved in some Bitcoin mining. And you know that the big issue is, at this point, the prices of Bitcoin mining in terms of technology have gone to a level that this is very expensive, but you actually cannot really make money if you count the electricity price. So in case your dorm administrators haven't figured that out, you get free electricity from San Jose State, so you can still make money on Bitcoin mining. But if you had to pay the electricity bill, you wouldn't even make money anymore. And this is exactly what's happening here, is that everybody thinks electricity is free because it comes out of the socket. The fact is, in aggregate, a billion times very little is significant on a national scale. So we really have two things happening. We have to figure out new technologies that are much more energy efficient in terms of semiconductors, and we have to think about what else will happen beyond US law. So these are two drivers which really say today we got to think beyond CMOS and look at other materials, and this will be a fundamental change in the semiconductor industry. So I'm not going to say much more about this here. We're doing material science. We're looking at new materials that could evolve in this. We're looking at architectures. There is a large center in Berkeley, which is actually an energy efficient computing, electrical engineering research center. So this is a driver, and I think this will become much more important over the next couple of years. Again, I talked about supercomputers in China. China has announced that they will try to supply their own semiconductors for their domestic market. There are only two export industries in the US which are traditional manufacturing that are still having an export surplus. So maybe I should sort of give you a pause and think about it. Which are the two manufacturing industries where there's an export surplus? One is aerospace, and the other one is semiconductor manufacturing. And if you talk to people in aerospace, they say the future of aerospace is semiconductors because it will be all electronics on airplanes in the future anyway. So investing in semiconductor development is a national imperative, and it's almost back to the late 1980s when the US government launched Sematech, because at that time all the memory chips went to Japan at that moment to counter that trend. And so we will need to see a lot of work happening here to think about what's going to happen in the post-Moore digital area. So let me talk about quantum. So quantum computing has been in one way or another around since the early 80s. Feynman said was sort of the first one to push this. I find that, for example, this Time magazine cover about the Infinity machine, which was talking about the D-Wave system. There's one D-Wave system with our colleagues at NASA that is run jointly by NASA Ames and the Moffett Field and Google. That was sort of 4 years ago, one of the big turning points that quantum really got exciting. The same Time magazine article also says, and nobody knows how it actually works. That's always a bad thing if you have a computer and you don't know how it works, because then the answers are unpredictable. But that was sort of the quantum magic part, and at that time when you were looking, I'm not sure if that's still true, but when you looked at Google image search for an image of a quantum computer, that's what you got, which is white guys in a white lab coat around this magic system. So there is some mystique around it. In between, things have moved forward. There are different ways of going about it. What D-Wave, the first one here, was doing was a particular technology, quantum annealing, which is finding the optimum of nonlinear functions. There's digital-based quantum computing, and there's quantum simulation. So a lot of people talk about the digital quantum computing. In Berkeley, we actually pursue what you might call analog quantum computing, which was actually what Feynman originally talked about it. And I'm not a quantum physics expert myself, but I have a very simple explanation what this is over here. In the mechanical world, there is something that's called an orrery, which I'm pretty sure does anybody know what an orrery is by any chance? No. Okay, but you've probably seen one of those. These are these mechanical devices. You have a crank, and you turn the crank, and then you have planets going around the sun, and you can shine light on it, and you can sort of look at how the planets align, and when you have an eclipse and all of this. And it's a completely mechanical device of the solar system. And this is, in a sense, a computing device for a mechanical system. You build a small model of a mechanical system that models to some level very accurately a much bigger mechanical system, the solar system. So think about the same thing what a quantum simulator is. You build a small quantum system that simulates, to some extent, the complex behavior of a larger quantum system. So you build a quantum computer that can simulate a bigger atom or molecule. And so in that sense, what we've done in Berkeley is we use superconducting qubits, and this is what this chart is. This is, on a 2-qubit system, we modeled a hydrogen atom, a hydrogen molecule, and modeled and computed the excited states and ground state for that hydrogen molecule. So this is using a quantum simulator to do a quantum calculation. That's significant because, coming back to my other old job as a director of a supercomputing center, if you look at supercomputing centers, half of the cycles are actually used to solve in one way or another Schrödinger's equations. So if you can solve Schrödinger equations more effectively on a quantum computer, that's a good solution. Now there's a lot of debate if quantum computers can do anything else. That's the result that I was just quoting. One of the, I think, wonderful aspects of quantum computers are these things that you can admire. These are wonderful. If you have a chance, look at one. These are actually not the computer. The computer are just chips, but that's called the refrigerator. That's the equipment and the apparatus that you need to keep the actual chips at almost 0 degrees. So they operate somewhere at the order of 1 or 2 degrees Kelvin. This is also interesting to keep this up here is that quantum computers, if they're going to be built, require a very different environmental setup that you need for a standard computer. A standard computer is very robust. You can roll a box in a room, you keep it cool, but you don't have to have super cool, and it's pretty much running. Quantum computers, in that sense, you have to have magnetic shielding, electric shielding, vibrational shielding, and you have very strict cooling requirements. So that's another thing that still is a big problem to be solved. I'm saying this because, going back and thinking about the digital revolution, the semiconductor companies and the computer companies don't tell you that there's a whole infrastructure in Silicon Valley of the types of companies like Applied Research who build the machines that build semiconductors that build computers. That type of infrastructure is not there in quantum computing. So this is a little picture. I'm clicking over this just to impress you that we have real things going on there. I have here two slides which are sort of meant to inform the current debate about quantum computers. And they are always stating out something and then giving a reply, and I can go through these. Certainly, quantum computers will never work as a myth. I just showed you results that actually show that quantum computers work and do very useful work today. There is sort of an industry myth that D-Wave, the first company to produce something, put out there and say they sell a compute solution system. That's not true either. They solve particular problems very well, but they're not a general purpose quantum computer. And you can go through this. There's just currently, in quantum computing, a huge debate out there. There's a lot of excitement. The meeting I just attended, of course, one question is, can we do machine learning on quantum computers? These are the Silicon Valley types who take one buzzword and another and throw it, stir it, and have a business plan, so they think. So there's a lot of that going on, but I believe it's a serious technology. It will complement, it will not replace, and I think that's an important thing. The myth is quantum computers will replace classical computers. That's not going to happen at all. Quantum computers will solve some new, different problems, and just like this picture I showed of the iPhone is, you can combine all those things from 1992 in one device, call it iPhone, but then once you have a device, then suddenly new thinking goes on, and things like, let's say, Uber were not thinkable in 1992. People could not just think about it. So the same thing is true about quantum computers. We will build quantum computers, they will solve a lot of problems really well, that will be the basis, and then people will think about new applications. So let me stop here at quantum and say a little bit more about the neuromorphic computing world. That's another thrust here. And I've done some work with colleagues right here, IBM Almaden in very south San Jose, almost in Morgan Hill. You probably know the place, somewhere up in the Green Hills there. And there's, of course, more behind this one bullet, but let me just say, make the claim here that based on some simulations that we've done in this work, I believe that you can simulate a whole, at least the sort of neurons and synapses and the electric process in the brain on a 1 to 10 exaflop computer with 4 petabytes of memory. And those are machines that will be available, as I showed, like the A21 machine in 4 or 5 years. The problem is that a digital computer that does that, even if it can completely simulate a brain, will require 20 to 30 megawatts. Now, if you haven't thought about megawatts, you may say, well, what does 20 or 30 megawatts mean? Well, you think about it this way. This means you have to pay an electricity bill per year of about $20 to $30 million. So you compare this to the human brain takes 20 watts. That's if you have LED, if you have to take an old incandescent light bulb, that's a very weak light bulb. So that basically means our brain is 1 million times more power efficient than digital computers today, more or less. That's a good number to keep in mind, maybe 10 million times, but just significantly. So this is an interesting thought here, and this is why what this thought, if you believe this for a moment, has to do with computer architecture and computer technology is that if you look for the Intel 4004, which had a fairly low clock frequency and a very low power density, and look where Moore's law took us, it took us in this direction. We increased the clock frequency until the gigahertz, into the low gigahertz range, and we increased the power density. And so technology was going from here to there. The interesting thing is our brain is just in the opposite direction. So the technology that has been pushed for the last 50 years, in terms of ever since Intel came into existence and Fairchild in the classical case of semiconductors, we're starting this trajectory with going in the opposite direction from where the brain is. And so you can say, well, what can we do? If we lower the clock frequency and lower the power density, what do we get? And this is what neuromorphic computing is all about. They're looking at non-von Neumann architecture, different architectures that are building massive connective networks, basically emulating the interconnectivity of the brain with large number of neuronal processors, which do just like the neurons in the brain, threshold computing. And there are a number of those out there. There were several startups that were launched in the last couple of years. Personally, as I said, I've worked with this group at IBM. They had a very nice processor. Important thing is that was done with traditional CMOS technology. It was actually not built by the actual thing that you see here was built by Samsung, I believe. But it's a remarkable 5 billion transistor chip that IBM built. So the interesting thing was that they can show on this type of chip that you can do an incredible low power processing and solve some cognitive tasks, including machine learning, at far, far lower energy budget than you would do on traditional von Neumann architecture digital computers. So here's some work we've done with IBM on the IBM True North platform in various different image classifications. So these are, you'd see, machine learning applications that run on those neuromorphic processors. There are some more, just to give you a sense, if you spot something of interest, ask me later on. And so I think there is a push here to use digital semiconductor technology to build different architecture machines. Now, the interesting thing is, in the last 2 years, I've seen now 2 companies right here in the Silicon Valley that are actually new computer companies, which hasn't happened in 15 or 20 years. The companies that have been launched in the last 15 or 20 years all were doing not new computer systems. They're computer system companies that use different architectures that are geared towards machine learning, that going in this direction to have much lower power. There's one company here, so I have non-disclosure, so I shouldn't say what their name is, but their selling point is, we will give you 1,000 times the performance of an NVIDIA Volta at only 10 times the cost or something like this. So they claim there's a factor of 100 improvement possible. These type of companies have basically decided to go in this direction, and the important thing is the trends in machine learning, the big commercial applications that are possible in the machine learning are driving this. So I think that is another interesting direction to go. Now I want to conclude this with a little bit philosophy, and this is from my own point of view and my own opinions. So I just want you to think about, beyond technology, about some other things. So this rise of machine learning created a lot of controversy, and you had some dignitaries and luminaries like Steve Hawking or Elon Musk, basically all being concerned about the machines taking over our life. And in one way or another, sort of this whole fear of intelligent robots making humans unnecessary, and that went as far, I think, that Stephen Hawking said this is the biggest event in human history, and it may be the last, because robots will replace humans. So I think, so my personal reaction to this is, and this is something I think you should form your own opinion and read things. It was driven by Nick Bostrom's book on Superintelligent, who really explored all these processes. My own thinking goes back, and I also want to show you this. So this is me at about 10 years old. Goes back to this thing here. So actually, you can look for it on the internet. It's actually still available. It's a basically a construction set that I had when I was 10 or 11 years old. And it was a plastic casing, and you could wire it up, and you had 10 switches or 12 switches up here. You had a light bulbs back there and batteries that were powering the light bulbs. And you could program this by wiring this thing up, and I could play tic-tac-toe against this computer or other things. So given how simple this thing was, it was a complete sort of wires, batteries, light bulbs, switches computer, but it was a computer. I figured out how to win against the computer in tic-tac-toe. It didn't take me very long. Probably wouldn't take you very long either. So it was very simple to win against. I mean, it's just you figure out tic-tac-toe anyway. So I won 5-6 times in a row against the computer. And then I stepped back and I said, wow, is the computer now upset at me? Is he, I made him a he, is he angry? And then it took me another 10 seconds. I said, no, it cannot. It's just a box with light bulbs and switches and wires and batteries and nothing else. So this thing does not have an emotional state. So this is, I think, the key insight. The fact that this is just a simple electromechanical device does not infer any type of consciousness or emotional state to it. So the problem is that, actually, sorry, there's a slide missing, is that there is an assumption that if you scale to larger and larger systems, somehow by some magic, very large systems would have a conscious, self-aware state. So you build a very big computer, that this computer in some sense suddenly gets the idea, I'll get rid of humans. And so there are movies out there that sort of pursue this theme, and you may have seen some of those movies. And I think if you really think through it, there is no way that a simple electromechanical or electrical device really can get to that level. Now, I make that statement, because you can debate at length, but I'll make that statement. After having made that statement, so I have a longer talk that just explores this and many other philosophical dimensions. But what I'm actually concerned about is subtle but different. These things are not evil. Computers are not evil, they're not good, they're just things. But the problem is that things which have no value will make decisions about our life. And that's, I think, the real danger. And the biggest example is the so-called flash crash that some of you may remember, which happened in, I think, 2010, where in the period of about 20 minutes or so, the Dow Jones completely crashed. There were some companies that, like Apple, that were sold at $100,000 a share. They were only sold at $100,000 a share because the automatic trading programs do not sell or buy higher than $100,000. It's just a hard-coded upper limit, which, as you know, in software exchange, you should never do that. But they do it. Unfortunately, it stops trading at $100,000. But you have to think about that. Some programs thought it was a good idea to buy Apple at $100,000, and some programs said selling Apple at $100,000 was a good idea. GE was sold at about 10 cents a share, so some computer programs thought GE is good to go, and whatever it was. But anyway, it was all high-frequency trading. What actually happened, we don't know. What actually there is a 150-page report by the Commerce Department, I believe, that looked at this, and they cannot really figure out what happened. It was just an unusual combination of several trading programs that interacted in a complex way that is not understood that created this phenomenon. So what I'm telling you about this is that in many of our systems today, we have a large number of complex programs making decisions that interact as a system of systems in a way that is completely unpredictable, that we can't do anything about it. And you've personally encountered this in many ways. You call your health insurance company, your claim is denied, and then they say, well, you have to call the supervisor who can override the computer. I think there's no more human in the loop. If the computer is the ultimate decision maker, we're exposed. So there's no intelligence there, but there's a huge danger of systems to make bad decisions. So what I'm really concerned about is, I'm also a science fiction fan, is in two Philip K. Dick novels. One is The Minority Report, and the other one is Blade Runner. And I'm really concerned about the Minority Report future, that we have a future where computers make an assessment and look at your nose and say, you're a criminal, we will take you into preventive detention. You are about to, whatever, do something bad. This is what the Minority Report says. And I say this because there are papers out there where people say, oh, we're using machine learning and we're looking at a criminal database and we're trying to see if there are facial features in the criminal database that will determine that somebody's a criminal. And you know, there's a lot of bias built into all this, in particular racial bias. And so what I'm really concerned about is not computers being evil and self-aware, but computers making autonomous decisions which are beyond human reach and which are based on some assumptions that are hard to be questioned. And so that's what I call the Minority Report future. As I said, there is a system in place which determines if somebody will be a criminal and will be arrested before the crime actually happens. So here's this picture. This is from what this IBM True North chip did. So it's a standard pattern recognition task, which looks at traffic picture from Hoover Tower. And the task was simply to determine are these pedestrians, bicycles, or cars. The important thing about this was that this was done in 200 times less energy than on a standard computer. So it gives you a sense of how much flexibility and power there is in sort of a neural neuromorphic approach combined with machine learning. And so my scenario that I think through is that you put this in a 7-Eleven and the camera sees you and tells you this guy is about ready to rob the store, stop him before you pull out the gun. So depending on which side of the debate you're at, you can find this terrible or desirable. So that's for you to think about as homework assignments. So in short, I think we're facing a time when, because of Moore's law, for CMOS devices will slow down. There will be big upheaval, unpredictable dynamics in computing. We'll get probably to exascale. We will have exascale systems. I think this is the last hooray of the traditional von Neumann architecture combined with CMOS digital processors. That will be great and wonderful, but we need to think now already. Machine learning is here and will have incredible growth path ahead of time. There are many scientific questions about machine learning that need to be resolved, reproducibility and really understanding the algorithms, but it's there and it's moving forward. I believe quantum computing will also evolve on a separate path, solve different problems, different from high-performance computing, certainly. I give quantum computing sort of this future of we have to figure out what it's good for, but if the infrastructure is there, smart people will. And high-performance computing, my traditional field, will integrate all of these elements into a different computational model. And as I said before, many of these things we're exploring currently in Berkeley at Berkeley Lab. And with that, I would like to leave it and thank you for paying attention. And I want to show you the last slide because we have the Workforce Development and Education Program, which does outreach, does many things from basically undergrad to faculty programs. There are programs to bring faculty and students in. They're all listed here. The website is there. I don't know what the application deadlines are for this summer. You can look at it. There are projects there, like, for example, undergraduate learning experiences. You can go not just to Berkeley Lab, but to any of the 17 different DOE national labs. So take a look if you're in any of the STEM fields. Would be very happy to see your application. And you can also ask me about things. So thank you.